Due to explosions of the Samsung Note 7 devices in 2016, almost 2 million phones were recalled, and production was discontinued. And this is not the only incident. Electric vehicles and other electronics have also had dangerous fires and explosions. But why did these batteries overheat and explode? Before we can understand why lithium-ion batteries overheat, first we'll look at their basic structure. Lithium-ion batteries have two electrodes, the anode and the cathode, with a separator between them. This separator is soaked in electrolyte, which allows lithium ions to diffuse and prevents the electrodes from conducting electricity to each other in what's known as a short circuit. A short circuit skips the terminals and connects electrodes directly, creating high current and excess heat. The first step in the overheat spiral, also called thermal runaway, is the initial generation of heat. This heat can come from several sources, one of which is short circuits. Separator penetration by an outside source like a nail, or lithium growths from overcharging, conduct electricity between the cathode and the anode. This short circuits the cell, generating high current and lots of heat. Another issue that can start this spiral is manufacturing defects. The picture on the right shows the manufacturing defects responsible for the overheating and explosion of the Samsung Note 7 phones. Insufficient space deflected the anode, compressing it, as well as large welding burrs on the cathode, which penetrated the separator, both contributed to the explosions. Manufacturing defects like we saw in the Note 7 can be difficult to pin, as the battery production process has many steps. Imperfections in the design or manufacture at any step could result in problems such as electrode contact, resulting in short circuit. Variations in the process and the environment means that there's an imbalance between cells in a pack, which can intensify during an operation. As such, it's important that batteries be tested for safety after manufacture. Another initial source of heat is an electrolyte oxidation. When charging a battery to too high a voltage, electrolyte oxidation can occur. This is where the electrolyte and cathode react to break down electrolyte and dissolve transition metal ions, generating heat in the process and reducing the long-term performance of the cell. The second step in thermal runaway is decomposition reactions, which produce oxygen, flammable gas, and more heat, creating a dangerous cycle. Once the temperature reaches around 90 degrees Celsius, the solid electrode interface, or the SEI, where the electrodes meet the electrolyte, decompose, exposing electrodes and producing more heat. Then, the lithium in the cell reacts with the electrolyte to form gas and even more heat. When the temperature reaches around 130 degrees Celsius, the separator begins to melt. Without this barrier, the cell short circuits, raising the temperature further. If the cell gets to as hot as 220 degrees Celsius, the transition metal oxide cathode begins to break down, releasing oxygen and substantial heat. This combination in a closed cell of extreme temperature, oxygen, flammable gas, and flammable electrolyte can ultimately lead to disaster. As shown in a test by Liu in 2018, battery cells eventually reach a tipping point of pressure and violently explode, catching the flammable electrolyte and released gases on fire. These fires are especially dangerous, as the only way to put them out is to flood them with a large amount of water. Many batteries have safety features to prevent dangerous conditions. To reduce reactions with electrolyte, a thin conductive coating of a material like aluminum phosphate or aluminum oxide can be coated onto a cathode. This layer prevents direct contact between cathode and electrolyte, reducing the heat-generating oxidation reactions. And when dangerous conditions occur, batteries can have yet another line of defense. Conducting layers within the separator, for example, can detect when lithium growth reaches the separator and can safely shut the cell down before short circuit occurs. Another commonly used feature are safety vents, which can safely rupture under pressure, releasing gas in order to prevent explosive failure. To review, high-temperature battery conditions arise from a variety of causes, like design and external factors, which can then cause a cycle of reactions which further heat the battery, leading to failure or even combustion. Initial problems can be prevented by adding coatings or protective additives, or the cell can be protected by shutting it down upon short circuit or by venting excess pressure. If you enjoyed this video, be sure to check out our video on lithium-ion batteries in cold temperatures, and stay tuned for more like this.